Alrighty, folks. This is the video lesson for section 2.1, and it's called Tangent and Velocity Problems. Alright, so the first thing let's do is discuss what we mean by the word tangent, okay? You've probably heard of a tangent function from trigonometry. That's not exactly what we mean here. It's kind of a different concept. So when we talk about a tangent, we're talking about a line. So tangent is going to be a straight line. Eventually, we're going to be concerned with finding the slope of a tangent line. It's going to be a big concept for this course. But first, we just want to discuss what a tangent line is to begin with, okay? So first of all, we've got to be tangent to something. So in other words, let's look at this first curve. We're trying to draw a circle. Looks a little like an oval, but let's say we've got that. And let's say I've got a particular point on the circle. So let me choose this point right here. And I'm drawing it kind of thick and large, just so you guys can see it. But really, that's just one little tiny point along the edge of that circle. All right. So now let's say I want to draw a straight line that touches that point, or touches the circle at that point, and only that point. All right. That's what we mean by a tangent line. And so, as you'll see, I'm going to use this little straight edge. There's really only one specific line that I can draw that's going to accomplish that. And let me show you what I mean by that. So before I draw it, I can hold the thing like that. And if you're seeing what I'm seeing, right, that's not really, I wouldn't say that's touching the circle at that point. I'm kind of touching this large dot that I drew. But again, that dot is just so visually so you guys can see it on the computer right there, right? That really just represents one little tiny touch of a point on the circle right there, right? So I've got something like that. So I want to make sure that I'm actually hitting the curve of the circle right here. So if I hold it like that right there, I'm actually kind of overlapping some of that dot right there, right? That is what I would call the tangent line right there. And so let me draw that straight line, and you guys can tell me what you think. So I think that looks pretty good. It kind of touches that point. The ink sort of overlapped there, but it's essentially just kissing it, right? So if you had a round object and you held a straight object against it, it's really just going to touch at one point. And so then you draw that line, you've got your tangent point. Notice this line now has a certain slope associated with it, right? We don't have any coordinates, so we're not going to calculate that, but there's some kind of rise and run associated with that line. And so when I say that's the only line that we can draw, notice if I start changing the slope of this thing, if I start rotating it, right, but want to maintain contact with the circle, then if I decide I want that slope, well, that's touching the circle at a different point, right? This might be the tangent line. If I draw the second line right here, maybe that looks like it's touching the circle at that point. Okay? So if we've got the same curve, but then if we specify different points, each point's going to have a unique tangent line. Okay? So that's important. So notice these guys are touching the curve. So the word tangent comes from the Greek language. Ancient Greeks studied geometry, invented geometry, you could argue, and came up with this idea of tangent or touching the curve at one point. All right, so it's not really crossing the curve. If I draw a point like here and go straight through it like that, right, you could say, well, this line touches the circle at that one point, but that's not really what we mean by a tangent line, right? So it's more like making contact and then kind of moving away in that direction, all right? So let's come over here and look at a different type of curve. Because what some people describe a tangent line as a line that touches the curve in exactly one spot, okay? And that is true. Sometimes that's true for circles. So if we get rid of that extra line right there, get rid of those examples, look back to our original example. I've got this point on my circle, and when I drew the tangent line to that point, it did in fact touch the curve at that one point, because then the circle's bending away, right? So this guy's extending in both directions right here, the line is. What if I come over here to a curve like this? So if I pick a point, let's say right there, and I want to draw the tangent line. First of all, we know it's not going to be a line that crosses the curve, right? We already ruled that out. So here I've got this green line right there. It's touching the curve at that one point, but that's not what we mean, intersecting and crossing to the other side. We kind of want to just kiss the curve right there and continue in that direction. So let me get my trusty little straight edge right here. Try to line that up. Let's say looks, if I'm blocking you guys, looks pretty good. Back it off a little bit because I've got this pen right here. And let me try to draw that straight line. All right. So there we have it. Got that black line right there is tangent to this curve, I would say, at that particular point. All right, there we go. Do you guys see, hopefully, where the whole definition, though, of touching the curve at one point at a single point falls apart. Where that falls apart is if this tangent line, lines extend in both directions, right? That's why we got these two arrows. If I continue this line in that direction, I'm going to cross the curve at another point, right? Because this curve sort of double backs in itself, right? It's decreasing and then it turns around and starts going back up. So you could say, well, wait a minute, is that really a tangent line? It's touching the curve at two different points. The answer is yes. It's tangent to the curve at this point, right? It's just touching the curve at that point. It's touching the curve over here, but now it's not a tangent line. All right. So that's what we've got. So when we discuss what a tangent line is, it's relative to a point that lives on the curve. That's important because we're going to look at another type of a line, which has another name from trigonometry, which is called the secant line. And that's going to be a little bit different, though, because, again, we have to specify what points we're at. But a secant line then is going to go through a point on the curve and touch a second point as well. Okay, so let me give an example of that. So not a numerical example. In class, we'll look at some examples from the book, and then on your homework, you've got the examples 2 and 3 are built into the homework. So you guys can calculate some of those. But let's just say I've got something like that, right? Kind of like a parabola. And let's say I want to put a point there, and I want to draw the line that's tangent to the curve at that point. That's one way of saying it, or you might just say the tangent line at that point. So let me get my straight edge and set that up. And that looks pretty good. So you guys will judge yourself when you're doing this at home, kind of get good to it. Again, I don't want to sort of tilt it like that. I'm not concerned with touching the big dot that I used to represent the point. I really want to kiss where the curve was at that point. Okay? So I'm doing something like this. And there we go. All right, so I've got my tangent line right there. Okay. And again, now that's a line in the plane, and so lines have slopes associated with them, right? That line has some particular slope. So recall that we use the lowercase letter m to represent slope, and so I could write slope or m, and with maybe a little subscript, m sub tan. Okay, so we don't know what that slope is because I don't have any values up here, but there's some slope associated with that line, and that's the slope I'm telling you guys of the tangent line. Okay. The problem with calculating the slope of a tangent line is what's our slope formula, right? So let's recall our slope formula. So if you've got the key here is going to be revealed in the question is if you've got 2 points in the plane, then you might label one of them. Let's call this first point x1, comma y1. So our x coordinate, our y coordinate. But then you need a second point. Right, because our slope formula would say change in y, so y2 minus y1 divided by change in x, so x2 minus x1. Okay, so there's our slope formula, but that requires 2 different points to calculate. Right, I can't just I can't say let me plug these coordinates into both of those things. Right, what happens if you try to do that? If I say y1 minus y1 over x1 minus x1, right? Just plug the same point in. Well, what's going to happen, though? You're taking a number, subtracting the same number. You're going to get 0 over 0. That's not a value, right? That doesn't exist. That's meaningless. So we have to find a different approach towards finding the slope of this tangent line. Okay, and so the way that we're going to do that is to use a secondary point that also lives in the curve and draw what's called the secant line connecting those 2 points. So let me draw a secondary curve. Where should I put that? Where should I choose this? I'm sorry, I meant a secondary point. Where should I choose that point to be? I want it to be pretty close, right? I don't want to go too far over here. Notice this line we would say, mathematically we'd say is increasing, right? As I move to the right, it's rising. So this line is increasing. So if I pick a secondary point over here and connect those two with a secant line, that's pretty far away, and I'm getting a negative slope right there. Which is okay, because eventually we'd want to move closer, but that doesn't seem to be a good approximation of this slope. So let me choose a second point, let's say up here. And again, I'm drawing, I should reiterate that. The point I'm going to choose on the curve is just this little green dot right there that I put. In other words, it lives on that curve. But when I do that, then you can't see the point that I'm drawing. So that's why I'm making these really large dots right here. Right? So these large dots are representations visual representations of just the one little tiny point that lives on the curve. And so what I can do now is draw what's called a secant line. So I'll write that word on the board, but that's just sort of connect the dots with your straight edge and draw your straight line. Okay, so we've got this green line up there, and that is a secant line. So that line is secant to the curve through this point, which is the point we care about, and then this secondary point. Okay, so that's cool. You'll see that this point, this line has some kind of slope, right? And it's got something in characteristic with the black one. It's an increasing line, right? But it looks a little bit too steep. So this slope, this value, if we calculate it, would be a little bit higher than the actual slope of the tangent line that we're looking for, but it's pretty close. Okay, so that's the concept of a secant line. Ultimately, what we're going to want to do in this class is get closer and closer, get a better and better and better approximation. So if we're saying the slope of this green line is an approximation, but not a great one, of the slope of this black line, how could we make that approximation better? And the answer is move that secondary point, right? We're concerned about the tangent line at this point. So this is kind of like our home base. But I can move my secondary point closer to this, right? So if I pick a secondary point, let's say right there, now what's going to happen when I draw the line connecting those 2 points? Okay, so again, let me try to set this up. Looks pretty good. And get this blue line sketched up right there. All right. Let me finish that line a little bit here. Make it look a little longer. Bear with me. Maybe you're graphing this at home, taking a minute to make it look all nice. And there we go, okay? So I've got this secondary point now, this blue point is closer to the original point. And what that did is it pulled the tangent line down, right? It's a little bit closer, a little bit more in line with the black line. Not perfect, but a better approximation. That's the idea. Ultimately, what we're going to do is take what's called a limit. So you'll see that the second homework, or the second section in the book, is all about limits. Remember, we can't ever make that secondary point live right on top of that point. We can't do that because then we get that 0 over 0 that we calculated earlier. So we can't do that. We always need a secondary point, but the further we are away, the worse our approximation is. So that means the closer we get, the better our approximation is. And how close can we get? That gets into the whole idea of sort of that there's an infinite number of points on here, on this curve, right? The original curve. So we can, however close you get, you can always get a little bit closer and then a little bit closer. And that's the idea, okay? So I won't go too much further on those topics yet because we still have to introduce limits. But that pretty much at least defines for us what a tangent line is and also a secant line, okay? So what you're going to see on the homeworks is a lot of these problems, what you want to do is take closer, you want to choose a secondary point, find the slope of that line, and then choose another point and find the better slope, and then get better and better. And so those calculations, I won't lie, they're kind of tedious. So you'll see on the homework, you might have these tables where you have to fill out 5 or 6 different slopes and see sort of what value they look like they're approaching. Right? And if they all look like they're approaching a certain value, then you go and say, well, if the slope is getting close to a certain number, then maybe that number is the slope of the line you're looking for. Okay? So that's the idea behind tangent lines, secant lines, and so forth. So that should get you going on the homework. Let me just discuss this whole concept of velocity, though. Throw that in, because that's a term from physics. So let's say I've got a table, or a set of axes like this, right? So typically we might call this the x-axis and the y-axis if we're in what we call the Cartesian plane, but we might relabel those sometimes for different physical quantities, which happens often in science and specifically physics. So let's say I've got something, so my time axis, right? So I've got time, which I'm going to put in parentheses the word hours. So time is my unit, but then there's a slight glare there, but that's just as hours time is my quantity. Hours is the unit that I'm measuring time in, so not minutes or seconds or anything like that. And then over here, I'm going to put distance, okay? And so, or displacement, I'm going to use the letter S for that. So that's kind of a physics term right there, or physics letter S. and let me put miles as my units. Okay, so I've got miles and I've got hours. So how does velocity come into play with tangent and secant? So let's say we're going to clock, let's say we were driving to campus. So I usually use this example. I know we're at home right now. Let's say I'm driving to campus. And so let's say I live 40 miles away from campus and it takes me 1 hour to get there. Okay, so here this distance is going to be miles from my house. So let's say I start at time 0 when I first get in my car, and then let's say I'm going to hit a stopwatch and then drive to work and then turn the stopwatch off. So when I get into the car, it's at time 0, right? The clock hasn't started, and my miles from my house is still 0 because I'm still in my driveway. So I'm starting right here at the origin, okay? And what did I say? I said that I'm going to drive 40 miles. So let me put a 40 up here. All right. And then how long did that take me? That took me 1 hour. So let me just put a 1 over here. All right. And so all I know is at this point is sort of the time and the distance from my house when I started. At time 0, I was 0 miles from my house. At time 1 hour, I was 40 miles from my house. Okay. And there we go. So this is where I was when I began. This point represents where I am at the end of that hour. So you guys tell me, if I drove, or if you drove 1 hour and you traveled 40 miles, then how fast were you going? Reasonable question, right? And so your intuitive answer would be 40 miles per hour, right? I did 40 miles in 1 hour, so I must have been doing 40 miles. I must have been going 40 miles per hour. And you could argue that that's true, but were you always going 40 miles an hour? I mean, there were probably some red lights, so you probably stopped sometimes. Maybe you hit the freeway for a little bit, went 60 miles an hour to make up some time. So your actual speed or your actual velocity was changing throughout your trip. But if you travel 40 miles in 1 hour, you would probably say average that you were going 40 miles an hour, which would be true. So what that average is, let's say I've got, how do I want to do this? Let me just draw the straight line first. And I'm going to pretend this is a straight line because my stick was not that long. But here, we've got this straight line, okay? If I calculated the slope of this straight line right there, then my slope, let's get our coordinates here. So here I've got the point 0, 0. All right, and then here I've got the point 1, 40. With their respective units and so forth. So if I wanted to calculate the slope, when you do physics problems or any type of problems, these science type problems that have units, honestly, the way I typically do calculations is I don't really include the units through my calculations because it's kind of just tedious writing. But it's definitely, you want to put the units at the end and for your final answer. Because if I said what's your average speed, you don't just tell me 40 what, right? 40 miles per hour. So we want to attach those units. If you're taking this class because you're a science major or something along those lines, where in those classes you're expected to do any kind of math work and show your work, in those classes I would show my units all the time. So if I were taking a physics class, I'd always be writing miles. So let me do that. So I'm going to do my slope formula here. So I'm going to call this x1, y1 and x2, y2. Okay, so I got my 2 points right there. So we said earlier, my slope is going to be y2 minus y1. So I've got 40 miles. Let me write miles, we're using m for slope, minus my y1, which is 0 miles. 0 miles, okay? And then my change in x is going to be x2 minus x1. So 1 hour, let's write hr, minus 0 hour, okay? You can already see why including the units all in the formula is a little bit tedious. So if I ever do ask you guys to show your work on a problem with units, you don't have to do it right there. But for your final answer, what do we have here? Now we've got 40 minus 0 miles. So we've got 40 miles over 1 hour minus 0 hours is 1 hour. All right. And then what most folks would probably do is separate at this point the units from the quantities right there and write this as 40 over 1. We've got 40 and then miles over hours or miles per hour, right? You might use the little slanted fraction line for that. So we're all accustomed to that. Okay. So there we go. So what do we see here mathematically and in terms of this example is that the slope of this line This represented my initial position, my starting position, and then my ending position. I drew the line connecting those two, the straight line, and every line is straight, but the just emphasizing that not a curve here, right? We just got a straight line, and we got 40 miles per hour. So that means the slope of this line is our speed, right? But what is that? Is that our instantaneous speed at different times throughout the trip, or is that our average speed? And we kind of argued earlier that that's our average speed. All right. So let me draw. I'll try to talk my way through an average trip that you might take to school. If you're driving, let's say you live 40 miles, you get in your car and you start. So time is going to be ticking. So I'm going to, as my hand moves to the right, that's time ticking from 0 minutes all the way through 1 hour, right? So 60 minutes later. And so the rate I take off, let's say I leave my driveway and I'm going through my neighborhood. Right, so my neighborhood has a slow speed limit, a lot of stop signs. So I'm kind of going through my neighborhood. I'm not speeding, right? There might be kids playing in the street, right? And then maybe I get up to a main road. I get up to Madison Boulevard and I go a little bit faster, right? Then maybe I get stuck at a light for a minute and I have to stop, right? So if I stopped, then time is ticking, but my distance is not increasing, right? So I'm kind of stopped at a light. Maybe it's a really long light, right? So I'm stuck there. Then, okay, now I get on the freeway. And on the freeway, what's the limit? 65, 75, whatever. I'm late for work, so I'm going really fast, right? So I kind of zoom up like that. Okay, and then I get off maybe around J Street or Fair Oaks and kind of slow down a little bit and end up where we know we ended up, right? 40 miles from our house, 1 hour later. Okay, so that kind of squiggly curve right there, that represents maybe the actual data or the actual sort of path that we took right there. Okay. So now, how can I calculate an instant speed, okay, or an instantaneous speed, you might say? So again, this slope right there, notice it was this curve, which now represents the actual path I took. So that's the data that we had from this trip. What we see in this straight line then is this straight line now is really actually a secant line, right? It's connecting this point, this beginning point and the end point. So that secant line right there is giving us the average velocity or speed. If I wanted to know my instantaneous speed, what I would do is use a tangent line. Okay, so let's say right at this minute where I'm speeding up, I'm going around that little, when you get on the freeway and you go around that little loop, right, you start building up speed because you're going to have to get on there. So let's say I'm going right there, I'm speeding up right here, it's getting steeper and steeper, and I want to see how fast I'm going at that moment. Then what I could do is draw that line. All right, and without finding some coordinates, well, this is a tangent line, right? So we argued already that we know that we cannot find the slope of that yet because we don't have the technique, and you could use approximations. But notice it's much steeper than the original line, right? Which means you're going much faster, right? So let me write the slope of here. Slope equals fast, right? Large slope. What about when I was in my neighborhood, right, or when I was driving on Madison Avenue? Then that point right there, if I draw the tangent line, not that steep, right? So if you can see the slope of that compared to my original 40 miles an hour, so I'm going less than 40 miles an hour, right? I know that because the value of the slope would be less than 40. So that's the concept. That's how velocity is involved in this section with tangent and so forth. Alrighty. So again, I'm going to kind of stop there for now. There's some examples in your homework that you've got. They should hopefully drive the concept home. They've got some nice graphs in there, perhaps better than what I've got up here. But yeah, so as always, send me any questions that you've got around this topic. And then the next video is going to be on limits, okay? And then I mentioned earlier, limits, that once we get the concept of a limit, we can start calculating a secant line, but pulling the 2 points, or pulling 1 point towards the other point, and pulling that average line right up to this particular line, and then we can get those instantaneous velocities that we're looking for. All right?